All right, welcome to the class again. Let me share my screen so that we have a look at the syllabus as we usually do at the beginning of the class. So there we go. We have covered most of the topics about week, including week 8 and above. So we have 9, 10, 11, 12. We can as well maybe bin 9 and 10 together. Let's see how it goes. Then probably spend a week for something else. That said, for now, we'd be covering some topics from week 12, as in today. I thought week 11 and 12 were more easier topics. So I thought let's cover that first for a change. As you see, from week 7 and before, it was one kind of a bin of stuff, one sort of a bucket of techniques that we were looking at, specifically supervised learning. So 9 and 10 is kind of different. 11 and 12 are different as well. So 11 is clustering, 12 is PCA and MDS, and it has some good use in exploratory data analysis and for visualizing data sets and stuff like that. These are more applicable, and clustering is very useful in general. It's used very popularly. So that said, let's jump into the class. But before that, I did get a couple emails yesterday, so I wanted to maybe touch base on that. So this is from Kamal. He said, so he basically said he tried to do KNN imputation. I know he was working with soft impute before too. And then apparently it seemed to have run initially, and then when he basically closed his session and came back, or maybe reopened the RStudio and then ran the code, he was probably getting some, he was apparently getting some errors. So this is something to truly help you on this, I should be able to replicate the error. So I will look into it in more detail. As far as the error goes, it seems to be looking like this: error in call names train, argument train is missing, no default. So also there apparently happens to be a KNN in a Vim package and KNN classification in another package. So this is imputation is what he wants to use. So it might as well be possible, since this is looking for maybe he's trying to do imputation, maybe the function that it's referring to is not the imputation function, but the same function from another package. So it looks like some sort of a minor bug or
that's
error.
What?
Yeah.
Yeah, Praneeth. So that's what I maybe when I was using initially, it was all running fine with the same exact command that I pasted there. But when I did the DMW data mining, and that I of Smart to implement Smart, but after that. And when I was running the SVM with the KNN variable, it was all working fine, and I was getting errors and everything. But
so usually
loaded everything, and when I was running.
So actually, before you got this error, or like before you just ran the statement, if you basically do help of KNN, it will give you the help manual, right? And then it'll on the top it will show what package it is referring to. So then you will know if the right package is being used or not. If not, you can also make sure you only load this package and not load this package, I guess. Or maybe
and even if you go to the help at the bottom, you will have a sample code, right? While I was running the sample package, I'm still getting the same error. I'm still getting the same error.
So the help did refer to the Vim help, or did it end up showing another help? Another case.
Refer to the Vim help.
Sorry, it chopped off. Can you say that again? I didn't hear the answer.
It referred to the Vim help.
Oh, it did refer to the Vim help. I see.
Yeah, and I removed the DMWR package as well, and still getting the same. So I exactly implemented the same that example that you were looking at.
Mm-hmm. This one? Oh, the code below.
Okay. In the function help.
I see. Yeah. Okay. So let me see the error once again. It says it is saying error in call names of train argument train is missing with no default. There seems to be no train argument here.
Yeah. And if you see the classification KNN formula, it has the train test variables in it.
Yeah, so that somehow tells me then there is some mess up that happened because of the two packages getting installed. Maybe the help is pointing to this, but in the end it's ending using this function, the KNN in here.
Yeah.
So yeah. Do you need this package for anything? For an
using Smart.
You're using that's what SMOT or SMOT.
That's unbalanced.
Yeah.
SMOT.
Yeah. For unbalanced classes. Yeah, I mean this is not something that usually happens, right? But it's definitely an interesting question because you have the same function on both sides. I'm pretty sure there will be a very simple turnaround to get over this. I will email back. I will check it myself and email, at least to have an understanding of your issue. So, yeah, I'll probably email everyone.
Yeah, thanks.
Okay. Yeah, cool.
The other email of compute, I figured it out. It was mistaken. So that's figured out.
Okay. Yeah. Perfect. And then let's see. Oh, this we have discussed last week. Is there any other email I have not attended to? Anybody else by chance, or anything else you want to ask here with regards to the project? Any concerns?
I'm working on the validating like how are the results like based on the last class. Did not make much progress, but I think I'll have some questions by the next week.
Okay, yeah, sure, yeah. I mean, this is a project that will literally go into your resume, so yeah, it's worth. Yeah, catching on to it. Okay. All right, so I guess that's yeah. Go ahead, Kamal.
Quick question. So when we are applying all this classification, any regression or any other model, we are taking the class versus rest of the rows. So for that formula, how do we determine that formula? Like how the dependency between the variables, whether we have to add, how many variables we need to take.
So is this, so you have a specific technique in mind when you're asking this, like when you're using a specific technique, or you're asking like in general? Because
some example.
Yeah, I think there was some topping. Yeah. Go ahead. If you were saying something.
So some examples I have seen, they were using variable 1 plus multiplied by variable 3. So how do you multiply?
Sure. It's not a multiply. It's basically an interaction term. So okay, yeah, I see your question. It's a good question, by the way. So it also is, the answer to this is kind of little technique dependent as well. So if you're using techniques like linear regression or logistic regression, then this question exists, like how do you figure out the right formula? And also, if you have even just 3 variables, you have many possibilities. You can use variable 1, 1, you can use 2, you can use 3, you can use a function of 1 and 2, right? This is like an interaction term. So you have a function of 1, so something that depends basically only on the singletons, then something that depends on all the pairs. Then you have, you can have pluses in the middle in the formula. Then we have something that would depend on like all possible pairs and then all possible triples, 1, 2, 3, right? Even for just 3 variables, there's so many possibilities you can use in the formula. So it becomes even more when you have like in real life data sets, like tens or hundreds of thousands of variables. So So in logistic regression, you literally have an error in trying to choose that feature selection. But for some techniques, there is inbuilt ways to do feature selection, like say random forest. A formula, you just pass everything in. So if you do variable importance, random forest, there you go. It will give you a list of, is an example coming from R itself. It's loading, but anyway, it will give you a list of the variables. Here, there's no variable names, just column names, not well named, but anyway, this is the point. So you have a list of which variables are the most important. So based on that, you can see these three are definitely very important, then the thing is decreasing at this rate. So you can have a cutoff, and you know what is the effect you're having on your cross validation error. So here it is inbuilt. You don't have to worry about the formula. You just feed it everything in. It will decide what it thinks are the important variables, and based on that, you can choose how many you want to choose. And then there is for similar things for SVM as well. You can pass in everything. It will figure out for the most part. But then there are some special situations. There is a line of work called feature selection methods, feature selection or variable selection methods. These are techniques that try to figure out what is the best subset of features that you need to use. And then once the subset comes out of the feature selection algorithm, then you use only that subset and then fit your technique. Sometimes these are useful as well. So it depends on practice of what technique you're using basically. For logistic regression, where you're spending the formula, then it is definitely a lot of trial and error. If you have a lot of time, you can try all combinations, but otherwise, you try a few things, and if you got some reasonable satisfaction on the error or the performance, then you stop there and go ahead with what you have. And in the future, you can start to refine it more. So yeah, it depends on the technique. Something like random forest would make it very easy though, because you don't have to worry about it too much. Does that answer your question, or?
Yeah, brilliant. So each algorithm has a different feature selection process.
Yeah.
Okay.
Yeah. Yeah. So there is also one more technique actually that is popular.
All right.
It's called MRMR, I guess. Yeah, MRMR. Minimum redundancy feature selection. Minimum redundancy, maximum relevance. So the overall idea, one thing to keep in mind, so you don't want to go into math and all that, but just for practical purposes, if you have variables like this is your data set or standard way we draw it, right? You have a lot of input variables, then you have output variable y. Basically, when you do feature selection, there are two objectives. It's not about one objective of figuring out what subset of features. One of the two objectives is you want to choose a subset of features from this part that is most dependent on y, right? That has most relation to y, because you're trying to use a subset of features, some subset of features that will help you predict y as well as possible, right? Using some function, some regression function that you will later build using whatever technique of your choice is as close as possible to y. Right. So that is one objective, but then there is another objective, which while doing feature selection, which is if there are features that are very similar to each other, similar columns, similar variables, you don't want to select them always, because then you're having redundancy, like too much duplicate stuff going on, right? Your increase in adding that additional feature is in your increase in your benefit in adding that additional feature in predicting y is very little, because what I have, if I add another feature that is very similar to what you already have, there's not much use. So you're just making a more complicated model. And probably you will also underperform because you're adding features that are almost the same. There will be terms in your model that will become like unnecessary noise once you fit your model. So the second objective, which I was talking about, is minimum redundancy, right? So you want the features, everything that is belonging to X within the subset that you're going to select after a feature selection, whatever your criteria is, those features have to be as independent as possible. So they should not be very dependent on each other, which means they're statistically independent, right? They're telling you much more newer things about predicting Y instead of saying the same thing again and again. So that is what this technique is saying. Minimum redundancy. You don't want same thing being selected, but maximum relevance to the response, basically maximum relevance. So that is also a popular feature selection technique. All these are available in R, Python, everywhere. So yeah, so that is one example of a feature selection technique. So you apply MRMR, you get some subset X star, that is minimum redundancy, maximum relevance. Then you apply SVM or NumPy, whatever your choice of technique. This is one way of doing it. But if you don't want to do an explicit feature selection technique, then you apply technique like random forest and then apply the variable importance routine. It will tell you after applying random forest on everything, then it will tell what X star should be. Also, there are other words for this feature selection. It's called filter methods, right? Filter method. There are different kinds, filter and wrapper. This is so filter methods are generally used as pre-processing step. So here MRMR is like a filter method. You first apply the selection of features is independent of any machine learning algorithm. So if you apply MRMR, nothing to do with random forest that you'll apply later. And then select something, then apply your technique. So that is known as a filter method. So there are many techniques that are filter methods. Where is a wrapper method, where the feature selection is dependent on the technique, the machine learning algorithm you're applying. So these are some different terminology. I'm just throwing them to say the same thing, but so that you also know the terminology around feature selection. So, okay, so we have that. Any other things you want to cover?
That should be all right. Thank you.
Okay, cool. So let's jump into the class. So since I said we will cover PCA and MDS, these are pretty popular actually. I want to do something a little different before I show those slides. I wanted to show you a plot I usually like a lot. PCA, crime. So let's say principal component analysis, crime. Then this. And let's do this. Yeah, this is the plot. Let's open the page itself. View the image. Okay, so I wanted to first show some result and then we can go back into the technique itself as for the slide. So this is the result, for example, of after applying principal components on a data set of arrests in US, so so regards to crimes and stuff. So this is similar plot again, another plot. So maybe this is even interesting, I guess. So I'll just do this. So there's another plot with regards to crime of different kinds. So basically, these red lines are the principal components. Your data, initial data is your different states. So if you see there are about 50 states, I guess, or maybe some of those states here. And then your X and Y axis are the principal components. This is basically some visualization of what is happening after projecting your data on the principal component. So this is the thing. Let's keep things simple first. So say I give you some data about crime across all these states. Then if you plot those states across those crime variables, you would not get this kind of a visualization. You will get something very different. But then you apply PCA on this data set, then you plot the same states again across the principal components instead of the variables that I gave you originally. So these will become my axis instead of some variables that are there in the original data set. But my rows are always the states, and my points are the states. My variables are now the principal components instead of the variables I gave you, instead of the features basically. And then if I think about it and see, is this telling me something interesting? Apparently in this data set it is saying apparently something interesting. Apparently if you go in this direction, you will be going through this blob of states where you have crime to do with more like urban crime, like street crime, urban related crime that you won't see in like a farm area or like in a rural area. then there is rape in these states is more predominant. Here, these states have more issue with assault. These states have more issue with murder. So this pattern would not have been as clear if you would have just plotted your initial variables. Sometimes it could have been. So this is the idea. What is PCA doing is you're projecting your data into a newer space of axes, newer set of variables, where there could be some newer ways of looking at the data where it would make better sense, where your data is explaining some phenomenon much better. That is the idea of PCA. So let's do some of this. So the intuitions of why we're doing it the way we are doing it. Yeah, this is another interesting classic example. So if I give you the data which has these circles, and this is the original data, axon next is the original data, not the principal components. Now the colored ones are the principal components. So this is the first principal component. If I want to use more than one, there's the second principal component. If you see the red one, which is the first principal component that has come after applying PCA on these circle data, on this dotted, on these dots, on these points, is basically the fact that your first line seems to be passing through your data set and covering most of its variance. The variability is in this direction. So most points are close to this line if you see from this direction, projecting them on this line. And then the second best thing would be in this direction. Because if you see there is more variability in this direction, this ellipse that I'm circling with my mouse. So that's the first principal component. Then the second most variance is in this direction, which is this part of the ellipse. So which is in the blue direction. So that's what the principal component is trying to do. It looks at the variability and the relations between the covariance between how the points are varying with respect to each other. And then you want to come up with a projection instead of these axes that you originally have, come with new axes, through which if you look at it, the first axis will cover most of the covariance, and the second axis, then the next highest covariance direction will be covered by the second axis. Then the third axis, if you think about it, here things are very close together, here things are more far off. So maybe some direction like this could have been the third principal component, for example, like that. Then the fourth thing might be like this, that's what PCA is trying to do intuitively. It's trying to preserve the covariance of the data set. Okay, so what we will do now is we will jump into some slides about PCA and how it is doing what it is doing, and then we will jump into the next topic, which is MDS after that. So let's start with PCA. So it's about dimensionality reduction in some ways, because originally you might have a data set with many variables, p variables, and n rows, n samples. But after PCA, if you want to use only two components, then k equal to 2, you're reducing the number of variables you're using. But there's some new set of variables. It's not your only. So it's not feature selection. Feature selection, you select some subset of features from original p variables. But this is like feature learning in some way. You're generating some new variables that will explain the data set as well as the original itself, or even better than the original data set. So you still have n rows, n samples. So n could have been the 50 states. P could have been some crime-related variables, but here there's a principal components in that plot. So k is the number of principal components you choose, and usually k is much less than p. So you have a much thinner, smaller data set than this big data set. Okay, so the residual variation. So what is the residual variation? When I showed you that plot with the red line and the blue line, whatever is not being explained by that is the residual. So in some way he's talking about variance and covariance in your data set, which we'll see more clearly. This is like a more generic statement. It's not very strict yet. It's definitely a very popular method. It was developed in much earlier. It's like a classic method in multivariate analysis and statistics. If you see these numbers, they're like really, it's a pretty old method. And these guys were really famous statisticians. And Carl Pearson established the first statistics department in a university in the UK, or maybe in the entire world, I don't know. Because before, the statistics was part of the math department, but then he separated into separate stat department the first time. Hotelling did a lot of popular stuff with multivariate analysis as well. So that's some history. So what is PCA doing in English words, right? Takes a data matrix of n objects and samples by p variables. The variables may be correlated with different amounts, and summarizes it by uncorrelated axes, which are your principal components. That's why they're like 90 degrees to each other. Each principal component is 90 degrees to the other principal component in the plots that you saw. So principal components are principal axes, and these are linear combinations of the original variables. So you take the original variables and you learn some combination of those original variables, which will give you the newer variables. The first K components display as much as possible of the variation among the objects. So this is the variance I was talking about when I showed you that cloud of points, the two directions of variation. So that's what it is trying to cover. So another way of thinking about the same thing. Objects are represented as a cloud of n points, like I showed you in that plot, in a multi-dimensional space. In that case, your dimensions were only 2, it is a 2D data set, with an axis for each of the p variables. So if you have p was 2, you have 2D data set. The centroid of the points, right? It's like a notion of mean, is defined by the mean of each variable, right? So it's the center point. The variance of each variable is the average square deviation of its n values around the mean. This is a standard definition of variance. What variance is basically the average square deviation from its mean, right? And that the degree to which the variables are linearly correlated is represented by covariances. So what is covariance? It's good to know. This is a very popular term, just like variance. So if the variability of a variable I is dependent on the variability of variable j, then that is known as covariance. So if j, whenever j is varying a lot, or maybe inversely proportional, but there is a strong dependency, right? Then the covariance is high. But when the variable j is varying a lot, it has nothing to do with how variable I is varying, and the covariance is low. They are not varying together in a similar way. It's similar to correlation as well, right? Correlation means these both are linearly dependent. You can draw a straight line that explains the relation between I and j variables. But covariance is a little better than that, because nothing to do with straight lines in specific, but just saying, are these things varying together in a similar way? So if I draw both the plots of both the variables, if you see when j is having less variance, if I also has less variance, or the other way around, I has completely high variance, and when j has less variance, it could be directly or inversely proportional. Either way, covariance could be proportional. But if there is a strong dependency, if I'm able to guess how it varies depending based on y, covariance is there's nothing that directly or inversely proportional, then covariance is low. Okay. So it's the few things that go into computing variances. The sum of all the n objects, the value of variable I in object m, mean of variables. So this is not very clear yet. We'll get into it. It's just used as part of the formula in general. So the objective of PCA is to rotate the axis of your p-dimensional original space, following properties. They are ordered such that the principal axis, whichever you call as the first principal component, has the highest variance, second has the next highest variance, and the third has the lowest variance. Now is a good time to look at that plot again. PCA, US, RS. It's good work as well. So this was a plot, right? So what's happening here is this. So if you look at the principal components, there is a better, I think this will be even a little confusing. Let's look at this example. It's simpler. This one, yeah, this is like a cartoon example, but it's perfect to explain. So if you look at the centroid is somewhere here. So if you compute it, because this is the mean across this direction as well the mean across this direction. Say for example there, and then the principal, if you rotate your axis in a way that the axis that passes through the most variance of the data is your first principal component. And the next variance is in this direction, highest variance. So this is your second principal component. So that is exactly what he's saying in these slides. Okay. So, here's some good plots too. So let's look at them as well. Okay, this is what we discussed. This is a 2D example. This is your data set. Variables x1 and x2 have positive covariance and each has a similar variance, which is true because you don't have, this is more circular than more elliptical, right? What do I mean by that? This direction, the variance is kind of similar to this direction as well, as against what we saw previously. It was more like one direction there was more variance, then the second direction has slightly lesser, somewhat lesser variance. The configuration, what the operation you do in computing PCA is you first subtract the means from both variables. So from a variable x1, you subtract its mean, from x2, you subtract. You're not changing the shape of your data, you're just translating your data so that the center is at the origin, which is what the case is here. So here, he's making sure this point is at the origin, because right now it is not. It's like 8.5 and 4.5, something like that. So now it is moved to the origin. The shape of the data stays the same. So it's translation. So that's what he said, by subtracting mean from each variable. Okay, then the principal components are computed. Now if you see, the data has rotated, right? Do you see the points? They have rotated slightly to the right, somewhat different direction. Here they're like this. Now the data has rotated. Okay, so say these 3 points probably ended up here. And then they have been rotated in such a way such that the first principal component, which is this axis, has the most variance being explained in terms of the data set. And then the next principal component is in this direction, which is the second principal component. So this is the PCA. That's what PCA is doing. And PC1 and PC2 have zero covariance, which means that's why these are orthogonal, which means they are 90 degrees, right? Which means you cannot predict PC1 from PC2. They're independent variables. So that's why these are like, you have another axis. Instead of your original XY axis, you have another axis that has zero covariance. So they're independent, but they're also explaining the most variance in an ordered way. Okay, so in practice, nobody uses PCA with only 2 variables, right? It's just a specific case, because if you have a data set originally of many variables instead of 2 variables, like 1000 variable data set, maybe you can project it to 200 variables or whatever you think is the right thing to do. So this is another example of PCA. This component explains the most variance in data, then the next highest variance explained by this component. And these two are again perpendicular to each other, statistically independent. And this is what he means by a term linear combination, which means if your original data was in y1 to yn variables, each principal component can be written as a sum of products of your original variables. y1, y2, so on till yn are original variables. A's are the different scalar coefficients, just numbers. So some linear combination of these variables will give you the principal component. You want to figure out what those are, while also satisfying that variance criteria that we're thinking about. Okay, so say your data set has 2 variables. When you compute a variance-covariance matrix, it is basically a matrix of covariances where the diagonals are basically the variances, because covariance of x1, x1 is nothing but the variance of x1. So it's just how variable the variable entries in x1 are. This is showing how variable the entries in x2 are. The off-diagonal elements are showing the covariance between x1, x2. They are obviously same because it's symmetric. Because covariance between x1, x2 is the same as covariance between x2, x1. So that's why these two are 3.41. This is known as a variance covariance matrix. Similarly, there is a correlation matrix, which is another concept, but we're focusing more on the covariance matrix. So this is the notion of, this is some basic linear algebra, right? You know what a matrix transpose is. You know what matrix multiplication is. So we don't want to go through that at this point. How do you compute the PCA in the end? We talked about what it is and what the interpretation is and what it is trying to do in terms of preserving the covariances and variances in an ordered fashion. But we want to know, how do you obtain those principal components? In the end, how do I obtain the solution, right? I give you a data set, how do I get my principal components so that I can plot my data in terms of the PCA? So basically the PCA is nothing but the eigen decomposition of your covariance matrix, and it's considering the eigenvectors as a principal component. So I don't want to bother you with too much math here, but there are a few things you definitely need to know, even at the highest level. So let me talk very quickly about the eigen decomposition. So I'm giving you a very high level overview. I do understand that fact, but let's start there. I mean, we can always get more deeper aspects of it. So you have a data set, say X matrix, okay? C is a function of X, right? Basically, N samples and P variables. So P is also P by P matrix, right? So if you have only two variables originally in your data set, then you have a 2 by 2 matrix C, which is your covariance matrix. And C12 will have covariance between 1 and 2 variables. C11 will have the variance of first variable, so on and so forth. C22 will have variance of second variable. C21 will be equal to C12, which will have the second variable. Now what they're saying is, to get the principal components, you need to compute the eigen decomposition. So the question is, what is an eigen decomposition? If you have a symmetric matrix, which is what C is, like because C12 is equal to C21, it can be written as a product of three things. Let's call it U matrix times lambda matrix times U transpose. This is the eigen decomposition. This is a theorem. And basically, this has some properties. U transpose to I by orthogonal. What is I? I is just an identity matrix. It looks like this. 1, 0, 0, 1. And what do I mean by orthogonal? Any matrix U that has this property of U transpose equal to I is orthogonal. But why do we call it orthogonal? Orthogonal usually says something like, it seems like, from an English point of view, like something that seems to be perpendicular is called orthogonal in general. So if you think about it, U transpose, if you open this matrix multiplication, if you still be 1 and when the off diagonals will be 0, the only possibility is like this. The concept of the angle between the vectors and an inner product, this is known as inner product, is as follows. There is this formula of inner product equal to norm of Ui times norm of Uj. This is a formula we have seen in, I don't know, plus in, I don't know, after 10th grade and maybe 11th or 12th grade, Ui, Uj cos theta. This is measuring this quantity. Here it is matrix multiplication, right? So this entry is Ui and Uj points as computing the norm of Ui times norm of Uj times cos theta. Can be 0 in the off diagonal between two vectors Ui and Uj. Theta is equal to 90 degrees because cos theta is equal to 0. Ui and Uj, what entries are there? This quantity U transpose will end up becoming 0. There are vectors that are perpendicular to each other. And VCT. And theta is basically the angle between the two vectors, right? So basically it is saying, orthogonal saying that it has perpendicular to each other. So these are basically your principal components are basically the columns of U or the rows of U transpose because you transposed it. So the first column is the first principal component. So this one. The second column in U is the second principal component. And they will always be perpendicular to each other, which is another requirement when I showed you that plot and all that slides. And that is also satisfied because of the condition that decomposition, this is eigendecomposition. And it will always matrix, not only the covariance matrix, will ensure that the eigen.
Hello.
I think.
Hello.
Hello? Yeah.
Yeah, got it. Yeah.
Was it muted just now or for a lot of time?
No, it just disconnected.
Oh, okay. I see. Okay. So, yeah. So, you did hear what I was talking about this slide, right?
Probably for the past
Hello?
2 minutes we. Yeah, Pranit. So probably for the past. It
okay.
was a little bit.
Okay. Sure. Yeah. Okay. Sure. So yeah, I was talking about how you compute principal components. The technique takes original data X, you compute the covariance matrix, and then you compute the eigendecomposition. Eigendecomposition exists for any symmetric matrix, and your covariance matrix is a symmetric matrix too.
Are you sharing?
Yes. Let's see. I think maybe something happened, I guess, because I was sharing till now. Can you see my screen? Hello?
Yeah, now we can see this.
You can see this, right?
Now we can see the screen.
Yeah, okay. Yeah. So yeah, I'm showing here how principal components are computed. So if X was your original data set, you take that. Say it has n rows and p columns. So p features and n samples. The next step to do principal components is compute the covariance matrix, which is the C matrix. It will be a matrix of p by p dimension, because if you have 10 variables, it will be a 10 by 10 matrix. If you have 2 variables originally in your data set, it will be a 2 by 2 matrix. The entries of the C matrix, the covariance matrix, are basically the covariances. So any entry ij will be the covariance between ith variable and jth variable in your original data set. So it's the concept of covariance. Then the third step is to compute the eigendecomposition of your covariance matrix, which is this. This is a very standard concept in linear algebra and matrix algebra, where any symmetric matrix, and C is one particular symmetric matrix, which is the covariance matrix, can be written as a product of these three matrices. It's known as the U, lambda, U transpose. Lambda is a diagonal matrix, so it only has entries in the diagonal, the rest are 0. These are known as the eigenvalues, the entries in the diagonal. The columns of the U matrix are known as the eigenvectors. So this is the eigenvector matrix. So any matrix will be exactly equal to the eigenvectors times eigenvalues times transpose of the eigenvector matrix. So this is exactly equal. So any matrix can be decomposed. So I can have U and lambda for any given symmetric matrix. I'll have a specific U and lambda, so that U lambda U transpose is equal to. There's also another property that is satisfied in eigendecomposition, which is that U and U is orthogonal. Why am I saying it is orthogonal? What is the definition of orthogonality? The definition is a matrix is orthogonal if it's multiplied by its transpose. So U transpose is equal to identity matrix. What is identity matrix? The matrix of just ones in the diagonal, rest are zeros. Orthogonal as an English word usually means perpendicular, and why is U perpendicular if U transpose is equal to identity? Where is the perpendicular thing coming from? So U transpose is nothing but dot product in vector algebra. Heard dot product and cross product maybe after your high school 11th. So it's the same dot product we're talking about. You take you're computing the dot product. So if you see this particular entry in the off diagonal, right? This is the entry of first row and second column is 0. Similarly, second row and first column. If you look at the 0 values, it is saying that the dot product between the first eigenvector and the second eigenvector is 0. And what is a dot product? It can also be written as the norm of ui, or the norm of the first eigenvector times the norm of the second eigenvector times cosine of the angle between the first and second eigenvectors, cos theta. Now, this is equal to UU transpose, especially this particular entry of UU transpose. Similarly, you can compute this entry or this entry, whatever you want. And this entries can only be 0 for between U1 and U2 here, only if this becomes 0, and this can only become 0 if theta is 90 degrees, because cos 90 is 0, which makes everything 0. Only then this condition can be satisfied, which is the same as saying that your columns in your eigenvector matrix U are perpendicular to each other. That is the reason when you plot the eigenvectors, they will always be perpendicular. You can plot U1 versus U3, U2 versus U5. As long as you're plotting two different eigenvectors, they will always be perpendicular to each other. The angle between them, if you look at the angle between them. So implicitly, because when I showed you the slides, we talked about the fact that your eigenvectors have to be explaining the variance, the covariance in the data, but they also are supposed to be perpendicular, which is this third condition, right? You have to explain the variance in an ordered fashion, which is what these two conditions are. But PC1 and PC2 should have 0 covariance, which means they're independent, which means they're perpendicular. This is being satisfied because the solution itself is coming from eigenvectors. And these eigenvectors are your principal components, and they, by definition, are orthogonal. So, which means the theta angle between those two will be 90 degrees, so they will be perpendicular. So one condition has been satisfied by saying that I will use eigenvectors of doing the covariance eigendecomposition on my covariance matrix. This condition is satisfied. I will always make sure that they will be perpendicular to each other. But how do I know that these two conditions are being satisfied, that my principal components are explaining my data set in an ordered fashion with respect to the variance? The first principal component explains the most variance, second principal component the second most variance. How do I do that? So that is being done because of another property, which is this. When I compute the eigendecomposition of my covariance matrix, so C can be written as U lambda U transpose. There is another property that is being satisfied, that we are minimizing distance between C and U lambda U transpose, right? So that is the same as saying this is equal to this. More and more minimum, the better. Then you have the solution, it will become your eigenvectors. So which means this quantity is nothing but, since lambda is a diagonal matrix, this is nothing but lambda. So if I'm looking at one entry Cij, one particular entry, for example, in my covariance matrix, this should be as close as possible to lambda I, lambda j, ui, transpose uj. So because it's just scalar values, you can always put it aside, bring the values aside, then first multiply u and u transpose, then multiply lambda. This is same as first multiplying lambda with u transpose, then multiplying u. You don't have to multiply in this direction because lambda is just scalar value. Since it's a diagonal matrix, you can bring it outside, then you multiply these two. So it's the same as this. So what this is saying is, it's basically saying that when you take a vector and multiply it with, say you had a vector like this, if you multiply with a constant number, it changes the length of the vector. If it's a small, it can either become a small vector, but it will be the same thing, or it can become a longer vector. It doesn't change where it is. It will always be here itself. It doesn't change the direction. It doesn't become like this. It only changes the length of it. So this is basically scaling your data in a way such that your covariances are preserved the most. I know this is a slightly complicated explanation I'm giving here, but basically you're preserving your covariances through your eigenvectors, which is what this is doing. But then the question is, am I supposed to use all the eigenvectors, right? If you use all the eigenvectors, then this will be exactly equal. But if I use only few, if I only need two principal components, then what you can do is, in eigen decomposition, there is this thing that is happening, another property. Your lambda matrix, which is a diagonal matrix, has only entries in the diagonal. The values are ordered in a decreasing order. Your first value will have the highest number, second value in the diagonal has the second highest number, third value will have the third highest number, so it's sorted in a decreasing order. So when I do this operation, when I'm saying Cij is the same as this, your lambda I, lambda j, if you use the topmost eigenvectors, then you will have the most explanation being done by the right-hand side with respect to the left-hand side. So what you can do is you can only use the two principal components, and if C was a P by P matrix because you had P variables, originally what your dimension would be is, and your X is N by P data, right? The dimension of your U lambda U transpose will be as follows. U will be P by P, lambda will be P by P, U transpose also be P by P. But if I use only two if I need only two principal components, what I do is I only choose P by 2. So I choose all rows but only two columns from U. I only choose two values, the first two values in terms of the diagonal matrix. So lambda will be 2 by 2. And U transpose will be again 2 by P, because U is P by 2, U transpose will be 2 by P. So that is one way. So since lambda is ordered in decreasing order, the only way I can choose if I want to explain the covariances only using two principal components, the best principal components I can choose are the ones corresponding to the first two columns in U, and the eigenvalues corresponding to the first, second values. If I want to use three principal components and the first three values, because it is an ordered values, they're ordered in a way that the first two will explain the most better way. The first three will explain the next best way. If I use all, it will explain the way, because it explains the C will exactly be equal to U lambda U transpose. Otherwise, there will be some approximation, some error will be left out. So that is the condition. So everything is coming from the properties of eigen decomposition. And if you just do eigen decomposition, this is very classical, very popular, and 90 do it in high school sometimes. But if you want to really understand the properties I used, all of these are present in here in the wiki itself. So if I say orthogonal, we have the orthogonal property. If I said the definition of eigen decomposition is like this: Q lambda Q transpose or U lambda U transpose. Where U is orthogonal, then I can also say there are more facts than you need, but this has everything in here that you need to understand eigen decomposition, right? So I'm using only few properties of this very popular concept. The fact that U transpose are orthogonal, and the fact that if I want any number of principal components, I only need to use those many number of columns in the same order that I have in U and lambda and U transpose the entries. Then I will get the best possible approximation of my covariance matrix. These are the only two properties I'm using to obtain the principal components. So the first one property is this, which is the approximation thing I was talking about. The second property is this orthogonal property, which makes sure these two are always perpendicular to each other. I know I threw a lot of math at you guys, but nevertheless, it's a very popular technique in data science, in statistics, and so forth. So from a practical perspective, how do you know how many principal components to choose for any given data set? So here they have some funny data set, the frog data set, for example. Originally it has 16 variables. Now the question is, how many principal components do I use? What people do is they usually look at the plot of the eigenvalues, because this determines how important any particular corresponding eigenvector is. So say in this particular plot, suddenly it drops till here, till the third principal component, then the drop is very little. This says just using three principal components will explain most of the covariance in your data. If you want to do much better, then you can keep adding this, but your incremental gain in explaining your data's variance in these directions will be much lesser. But these three principal components will explain most of the directions in your data. So basically you do a plot of your eigenvalues and then choose where this threshold would be. The drop is the highest. Till there you use those many number of principal components. Yeah. So that's the PCA. From a practical perspective, as far as our coding goes, it's calling a function called print. Did I lose you in the middle? Okay. So this is the function, the print comp function.
For Pranit, for me, the screen got stuck.
Oh, okay. Did it get stuck just now or a while ago? Because if it stuck a while ago, it would be better you would have told me then. Yeah.
I was still looking at the PowerPoint.
Oh, okay. Okay, but you were there in the discussion we had with respect to this, right? Yeah. Okay. Okay. So it was just then now. So yeah, all I was saying is, yeah, eigendecomposition has so many properties, but we are basically only looking at using these two properties when we compute PCA. One is this, that your principal components have to be, which is satisfied by eigendecomposition. They will be perpendicular. The other property is, if you want to use only two principal components, the best principal components to choose that will explain the most covariance will be the first two principal components, the first two eigenvectors. If you want to use three, then there will be the first three eigenvectors. If you use all, it will explain your covariance matrix exactly the same. That's what it is saying. And as far as coding goes, it's much simpler. You've been listening to here. There is this function called printcomp. It's in the base package itself. You don't have to install any package. You just pass and comp of you or whatever your data. So, yeah. There we go. We got the PCA plot. So these are the values. So, and how much variation if you use much of it. Some data sets
I think there is too much
yeah. I think hello.
Yeah, Pranit. Screen got
screen got stuck, and the last few minutes it got chopped off. Your voice is still breaking.
Hello?
Hello?
Yeah, I couldn't.
I don't know why it's chopping out. I'm not sure if it was somebody else.
No, I doubt actually the Thiru, Kamal and Manish are here or not.
Yeah,
No, we are with you.
we are here.
Yeah, now we got
Okay, yeah.
Like.
Okay, yeah. I'm not sure. The internet, I think, is bothering a bit today. Yeah, I think Thiru was asking some question. I know someone was saying it got stuck as well. I heard this choppy voices.
So we couldn't hear the last part when you were trying to explain the coding part, Praneeth. We missed all of those sections.
Oh, okay. So that should not take long. I was saying it is super simple function call. Let me show it again. Present to everyone. So just one single function call. You don't have to do anything about it. Additional. Just pass your data set into it. It's called the print comp. You can see my screen now, right? So this is the manual of the function, the help. So there is they use the USRS data set as part of the example 2. So if I just copy paste it, I don't even have to copy paste all of it, but I'm just doing it for now. So this is the same USRS data set. You get that plot, and if you go back, you also get this plot. This is the plot of how the eigenvalues and eigenvectors and how much variance they're explaining. So this tells me the first two principal components will explain most of the covariance in my data. So in this particular data set, the third and later won't give me too much information. But sometimes in some data sets, maybe, because these were the biggest, right? You see the biggest thing is being covered by these two, then it's not covering much. In terms of explaining the variance. But maybe some data sets you would need, maybe your data set is 100 variable data set, maybe you need 7 principal components. It depends on this plot. But it's as simple as just calling comp on USRS. And that's how it works. And then you can also plot the result of it with respect to the principal components by just using the plot command. And this is what it returns. The same numbers are returned here. And different way where you use and then see how those variables lie and your data is rotated with respect to the principal component, which is this one, right? So the original variables, the red ones like this system, and finding the right principal component so that the X explains the most variance. Then if you see, get these new nice interesting patterns, it begins to show. These could have as well been like sometimes in classification for data sets, like some labels. Then you can see nice directions that, oh, in this direction it is explaining spam email, this direction no spam. This direction in terms of what the principal component is explaining in terms of the original variables, for example. So yeah, but the bottom line is you just pass your data frame. I'm not sure it should be data frame or matrix. If it's in the right format, then if you just pass it into print comp, it will start working. When you do the plot and the result of it, you will get these plots as well. Yeah, that's all I was saying. Yeah, so I did throw a lot of math at you. I'm aware of that, but it's an interesting and very popular concept. Everyone knows about PCA, so it's worth sharing it. And then it's been applied to a lot of areas like face recognition, for example. So if I did say PCA face recognition, the technique is called eigenfaces. I think this guy is like a professor. I think he's still in MIT, so it's a very popular technique. So they basically compute the eigenvectors of the covariance matrix of your images instead, because your input data is face images. And then they use the distance from your eigenvectors from the PCA representation to say if the face is matching or not in terms of the face recognition. And this basically is just a direct application of PCA on face data sets, and it apparently used to perform very well in terms of recognition. In these applications, right? I mean, I'm not saying it is the solution for every problem, but it did work very well in a lot of data sets. You can always find improvements of what PCA does not do well and what other technique will do better than PCA. But see the pipeline for eigenfaces. You have a lot of images, for each image, you are if it's like a K by K image, right? If it's like a 256 image, whatever the size is, you just arrange all the values as if it's not a matrix anymore, but it's like a single column. Then you get each column will become one particular image. So this image becomes one column in your data set. This image becomes another column. So if you have m images and each image is K by K, your newer data set would be K squared by m, right? So then you apply PCA on this, and then you do face recognition based on how far it is from the PCA representation, right? So there's nothing but PCA applied. This is another nice technique. So PCA is very popular. So it's known to a lot of people. So it's usually part with respect to stats and data science, or applied stats in general. So that's the reason I shared this technique with you. Since you can also email me once you do some reading about these topics. You can also think of doing taking a face data set and doing some face recognition and adding it in your resume. If you want to do it with respect to PCA, you can call it Hugging Faces. This will give you ideas, right? You can feel free and explore applications as well. All right. So yeah, I mean, we'll pass a little bit of our usual time as well. So yeah, I'm calling it a day. Have a good weekend. You can also email me with questions and stuff, but keep working on your project quickly and make sure it ends up in your resume in a good form. Okay, thank you. Bye-bye.
Thank you.